Yeah, so let's start with today's session. This today's week 8 of this live NPTEL sessions. So today I'll be covering slope deflection method. Okay, as the name suggests, the unknown which we could find using this method are slopes and deflection, and after finding out the slope, we can also find the moments. Okay, so first, I will tell you a brief theory about the slope deflection method. We'll not go into the details of the derivation of these equations and all. I'll just tell you the equations which we need to use, the sign convention, and how to apply these equations to get our answer. Then we will see one table for fixed end moments. After that, we'll see some questions of gate, and lastly is one practice problem. Okay, so let's start with today's class. So, what is the slope deflection method? So, slope deflection method is a method to analyze the indeterminate beam. You just need to remember few things which can come for the MCQs and all. So, slope deflection method is a method for analysis of indeterminate beams. For the determinate beams, we can easily find out the moments and everything by using the equilibrium equations. But for the indeterminate beams, we cannot directly use the equilibrium equation. So this method is proposed, which through which we can find or we can analyze the indeterminate beams and frames. So slope deflection method is a method to analyze the indeterminate structure. That is the first point. Second point is, as the name suggests, the unknowns in this case are slope and deflection. Okay, this method accounts for flexural deformations but ignore the axial and shear deformations. This is also a very important point. Once this once a direct question came from this point in engineering services examination. Okay, so the assumption while deriving these equations of slope deflection method, we assume that only there are flexural deformations. Why only flexural deformations are considered? Because axial and shear deformations are very small as compared to the flexural deformations. Okay, so while deriving the slope deflection equations, we account only for the flexural deformations and ignore the axial and shear deformation. This point can also be very important for MCQs. Okay, so please note these some important points down. Another thing is the sign convention. We will use clockwise moment as positive and we will consider clockwise rotation as positive. Anti-clockwise moment and anti-clockwise rotation will be considered as negative. So this is the sign convention we will use. Finally, the slope deflection equations. So slope deflection equation is a relationship between the end moments and the slope and deflections. Okay, so these are the two equations, so we can write it in an easy way also. Suppose there is a beam. Let's consider a propped cantilever beam. It is having a span A and span AB. Okay, so we can write the slope deflection equation as, please listen to this carefully. So MAB and MBA. So we are finding a relation between end moments and the slopes and deflection at different points. So MAB at the joint, sorry. So MAB is MFAB plus MFAB is the fixed end moment. MFAB plus 4EI theta A. So theta A, 4 will come with the first term. So here MAB. So A is the first term. So 4EI theta A by L plus 2EI theta B by L minus 6EI delta over L square. So this is the equation for MAB. You have to remember this equation. Next is MBA, that is end moment BA. So MBA will be MF BA plus, here B is first, so we'll use 4EI theta B over L plus 2EI theta A over L minus 6EI delta over L square, where MFBA is the fixed end moment due to the external loading. Okay, so these are the two equations, very easy equations to remember. Okay, so now we will solve all our problems using these two equations. Here MFAB I've already told, it's a fixed end moment. What is theta A? Slope at A. Theta B, slope at B. And what is delta? Delta is the amount by which any support sinks or settles. Okay, here in this case, I've already told the sign convention for moment and for rotation. So what would be the sign convention for this delta term? Okay, so this delta term will be positive if the right hand, the support which is on the right hand side settles. So support at the right side is support B. If the support B settles in downward direction, then this delta we will consider as positive. Okay, and if this support at A side, or if the support A sinks by delta amount in downward direction, we will consider it as negative. So this is the sign convention. You just need to remember this point. If the right hand support sink downward, it will be positive delta for MAB also and for MBA also. Okay, so this is all the sign conventions. Theta A and theta B, if they are in clockwise direction, they will be positive. Delta will be positive if the right hand support sinks by in downward direction. Otherwise, it will be negative. I hope this is clear. So till now I've just discussed the slope deflection equations and the sign conventions for it. Now we will see what are the fixed end moments. So fixed end moments are nothing but the moment generated due to the external load when both the ends of the beam are fixed. As the name suggests, fixed end moments. So fixed end moment are the moments generated at the ends when both the ends of the beam are fixed. So we can also derive the fixed end moments. We can calculate the fixed end moments using different methods, but we should remember the some terms, like some of the cases we should remember. For example, this is a huge table. You do not need to remember all the things. Just don't ignore this part where one end is hinged. Just concentrate on this part. You should try to remember all these fixed end moment terms. I like to zoom it somewhat. Yeah. So out of all this, if you can't remember all the terms, all the cases, then you should remember at least this case where the fixed end moments are calculated for a point load, or and this case where the fixed end moments are calculated for the UDL. There is one more case which you should remember, that is this case where the fixed end moments are for the triangular loading. Why this case I'm saying? Because for one direct question came in engineering services examination 2018. I'll show you that question. This was the question in which the direct question. So a fixed beam is loaded as shown in the figure. So we need to determine the fixed end moment at the support A. Okay, so if you would have remembered this table, at least these three cases, then you could solve this question. Okay, so the first is the fixed end moment due to the point load. The fixed end moments are given here. If you want, you can note that. Fixed end moment due to UDL, these two are the cases, and fixed end moment due to the triangular loading. Okay. Yeah. So as I've told, one direct question came in engineering services examination. So they are asking the fixed end moment at support A. So if we see the triangular loading case, so fixed end moment at support A is WL square by 20. So the answer here will be B, option number B, WL square by 20. If you can't remember the whole table, three cases at least you should remember. Okay. Then Now we can solve some gate questions using the slope deflection equations. So this question came in GATE 2001. It's a 5 mark question, although in these years these type of question doesn't come that much marks of question. But so in this question, here is a two span beam is subjected to a clockwise rotational slip of 0.004 radian at the fixed end A. Applying the slope deflection method of analysis, determine theta b. So we need to determine theta b. So this is a two span beam which there is no external loading. Okay, it's a two span beam with no external loading. There it is given that the support A slips by 0.004 radian. So that is the okay. So the support A slips by 0.004 radian. There is no external loading, and we need to determine the slope at B. Suppose for this beam, if this support slips by some amount, so it will affect the rotation of support B also, right? It will cause the rotation in support B also. So they are asking what would be the value of that slope. Okay, so this is the question. So the support at the angle, the rotation at B could be either due to the external loading or due to settlement of support or due to rotational slip. But in this case, there is no external loading. It's just that this support A slipped by 0.004 radian. It looks like a complicated problem, but it's very easy, you'll see. Okay, and after that they are also asking us to determine the end moments. Okay, in if in any question in GATE, if you are asked to determine the slope, you should know that you have to use the slope deflection method. If you are asked to find the slope in a beam, then it's better to use the slope deflection equation. The question will become very easy. Let's see how. Okay, so we know the slope deflection equation. Let's make this beam again. If I'm going very fast or very slow, please you can stop me at any time. Okay, so it's a two span beam A, B, C. If there is no loading, there would be no rotation at support B. Okay, but here this the due to some cases or because of some accident, this support A slips by theta A amount. Okay, and because of when it slips, so this would be a probable deflection profile of it, right? So there will be some rotation here at theta b also, right? So they are asking the value of this theta b. Okay, so let's see how will we use this slope deflection method to solve the problem. So let us write the slope deflection equations for all the spans. So how many spans are there? Two spans. So how many slope deflection equation we can write? Four. Okay, two span, so two for each side. Like MAB, what would be the value of MAB? It will be MFAB, that is fixed end moment at AB, plus 4EI theta A or theta B? Theta A, right? Because it's A is coming here first. So theta A by L plus 2EI theta B by L minus 6EI delta over L square. So this is the slope deflection equation for AB, MAB. Now let's see which of the terms are known to us. Okay, so MFAB is the fixed end moment AB due to external loading. In the span AB, there is no external loading, right? There is no external loading, no load is applied here. So MFAB term will be 0. Okay, now theta A, but sorry, this and A is a fixed support. So if there would have been no rotational slip, then theta A would be 0. Okay, but here it is given that there is a value of theta A due to the rotational slip. So theta A is there. Okay, let's see, theta B will also be there, right? Because it's a hinge support, so rotation will be there. Now let's analyze this last term, which is 6 EI delta over L square. Delta is a term which comes whenever there is a sinking of support or the support settlement. But in this question, it is given nowhere that any support is settling. So this term will also be 0. Okay, we just have these two things. Let's write it for MBA also. MBA will be MFBA. Similar equation. 4EI, here B has come first, so it will be 4EI theta B over L plus 2EI theta A over L minus 6EI delta over L square. Similar equation as the first one. So in this case also, there is no, no external loading. So this will be 0. Theta B is there, theta A is there. Delta is not there, so this is also 0. Right? MBC. Let's write it for MBC. It will be MFBC plus 4EI theta B, right? Because B is here by L plus 2EI theta C over L minus 6EI delta over L square. See, these equations are very easy, but you should see the terms or the sign conventions that might be there. In that case, there might be some mistake. Okay, so MFBC is not there. Why MFBC is 0? Because there is no external loading in the span BC. Theta B is there. Theta C will also be 0. Why theta C is 0? Because C is a fixed support. So theta C is also 0. Delta is 0, also 0. Why? Because there is no settlement of support. Right? Okay, so I think these equations are fine. We can also write it for MCB if you want. So let's write it for MCB also. Okay, so MFCB plus 4EI theta C over L plus 2EI theta B over L minus 6EI delta over L square. Okay, so in this case also MFCB will be 0, theta C will be 0, delta term will also be 0. Okay, so we have written all these 4 equations, slope deflection equations. After writing, so first step is write the slope deflection equations. The second step is use the equilibrium equation to solve these equations. So here the equilibrium condition will be the summation of moment at any point is 0. Okay, so equation is, we know this equation, right? Summation of moment at any point is 0. This is one of the equilibrium condition. So we will use this equilibrium equation to solve these equations. Okay, so the equilibrium equation is, so we can use the summation of moment at point B is 0. Let's write it. Summation of moment at B is 0. So what are all the moments at B? MBA. So at B, the two moments are MBA and MBC, right? MBA plus MBC equal to 0. MBA we know. MBA is 4EI theta B over L plus 2EI theta A over L. Right? What is MBC? You can also try to solve with me. So MBC, there is only one term, that is 4EI theta B over L. Right? So we have used this equilibrium equation for solving the value for theta. So we know theta A here, right? Only the unknown term here is theta B. So we can solve it as 8EI theta B over L is equal to minus 2EI theta A over L. Right? So solving it, we can write as theta b equal to minus theta a by 4. So what is the value of theta a? Theta a is given as, theta a was given to us, and the value of theta a was 0.004 radian. So we get the value of theta b as minus 0.001. So this is the value of theta b we got. So first part is solved. Okay. In GATE, if you have a lot of practice, you know that at the end you have to apply the equilibrium equation. For applying the equilibrium equation, you need MBA and MBC only, right? Because here I was using MBA plus MBC equal to 0. So you need not to write all the equations. You can just write for MBA and MBC and add them and equate it to 0. Here we can find the value of theta b as minus 0.001. What does the minus sign indicates here? The minus sign indicates that the rotation is in anti-clockwise direction. Because we are considering clockwise rotation as positive, we got our answer as minus 0.001 radian. So this will be anti-clockwise rotation. So either we can write as like this, or we can write it as theta b equal to 0.001 radian in anti-clockwise direction, like this. So these are the two possible cases. Okay, now this answer comes in radian. Please note that the answer is in radian. Whenever you solve this equation, the answer is in radian. But sometimes they can ask you that what is the rotation at the end b in degrees. So then you need to convert this radian into degrees. Okay, so this thing you should keep in mind whenever you are solving the fill in the blanks type of questions. Okay, so whenever we solve these equations, we always get the answer in radian. Okay, so in this question they asked what is theta b, so slope at b. So we have already calculated theta b. Now they are also asking what would be the end moment. So end moments means MAB and MCB or MBA, all the things. So here now we have to use these all these equations. So we can put the value. Now we know theta A, we know theta B. We can put the value of theta A and theta B in all these equations, and we can find MAB, MBA, MBC, and MCB. Okay, so can anyone tell me the value of MAB quickly? You know the value of theta A and you know the value of theta B. Please try to solve it yourself. So I'm also doing it. So MAB was, so equation was 4 EI theta A by L plus 2 EI theta B by L. So we can write as 2 EI by L, we can take common, and we can write 2 i's of theta A plus theta B. Okay, so these type of questions, please try to solve it with me. Otherwise, this won't help much. Okay. So now another important thing is to check the units. Okay, so here either to use everything in kilonewton meter or use everything in newton and mm. Otherwise there might be some mistake in units. So this will cause very much problem in case of fill in the blanks type of question. For MCQs it will be fine, but in fill in the blanks type of question it will be difficult for you if you do not care about these units. Okay, so in this case the value of EI is given to us. So EI is 25,000 kilonewton meter square. Since EI is given in kilonewton and meter, so let's take everything in kilonewton and meter. Okay, so it's 25,000 kilonewton meter square. So for this question I'll take everything in kilonewton and meter. So length I'll take in meter, and length was given as 5 meter. So I'll put 5 here. Twice of theta A. So theta A was 0 plus 0.004 plus theta B was minus 0.001. So from this we can calculate the value of MAB as, so solving it I'm getting it as around 70 kilonewton meter. Okay, so units are very important, otherwise it's very easy. Okay, similarly you can find MCB also. So mcb is equals to 4 ei theta c over L plus 2 ei theta b over L. But theta c is 0. Why? Because it's a fixed end support. So theta c is 0. Only 2 ei theta b by L. So solving it, we get the value of mcb as, let's put the value 2. What is the value of ei is 25,000. What is the value of L in meter? 5. What is the value of theta b? Minus 0.001. So the final answer we got is mcb equal to minus 10 kilonewton meter. What does this minus sign indicates? The minus sign indicates that this moment is in anti-clockwise direction. Okay, so the, using these equations is fine. Just you need to keep in mind the sign convention and the units. Otherwise, it's very easy. So this question looks like very complicated, but it's very easy if you use this slope deflection method. Okay, so whenever in the question you are asked to find the rotation or slip or anything like that, you should use this slope deflection equation. So there's another question from GATE 2017 of set 2, question number 42. So in this question, there's a portal frame which is given to us, and the value of E and I is given, and you need to find the rotation at joint Q. So here also we need to find the rotation. So whenever you are asked to find the rotation, just simply use the slope deflection equation. Okay, so let's see how to solve this question. So this is the frame which is given to us. So before solving this, let us simplify this problem a bit. Okay, so in this question there's a beam and one column like this. So this is the main problem. Another thing is this span PQ, this we can remove, and we can instead of this loading we can apply moments here. Because of this loading there will be moments, right? So we can make an equivalent system like this for analysis purpose. What we can do, because of this 2000 kilonewton, what would be the moment at Q? So moment is force into distance, right? So because of this 2000 kilonewton force which is at 2 meter distance from point Q, what would be the moment? What would be the value of the moment? The moment will be in this direction, because it is rotating it in anti-clockwise direction. 2000, just focus on this 2000 first. So 2000 into 2, it will be, the moment will be 2000 into 2, which is 4000 kilonewton meter. Another loading is this 161650, okay, 1650. But this 1650 loading is rotating this system, is causing the moment in clockwise direction, right? This is pushing it in this direction, right? So it is a clockwise direction. So here the moment developed would be in clockwise direction. And what would be the value of the moment? The value of the moment will be force into distance. So force, total force will be 1650. It's a UDL. So value of UDL into length, that is 2. And at what distance it is acting? It is acting at CG of this loading, and the distance between this Q is 1 meter. Please stop me at any point if you are having any doubts. Okay, this is for session is for you can ask me anything. Okay, so this is causing it 1650 loading is causing the rotation in clockwise direction. And what would be the magnitude of this moment? The magnitude of this moment will be force into distance. So this distance will be the distance between the CG of this loading and that point, which is 1 meter. So solving it, we get around 3300 kilonewton meter. Okay, so this we have removed this loadings, and we have, instead of these loadings, we have applied the moments here. Okay, so we can do that for analysis purpose. Okay, so what is the final moment we are getting? Final moment is 4000 in anti-clockwise direction and 3300 in clockwise direction. So final moment will be 44, sorry, 4000 minus 3300. So it will be 700 kilonewton meter. In which direction? In anti-clockwise direction. Why? Because 4000 is having the greater value. Okay, so equivalent to it, we can just remove everything and apply the loading 700 kilonewton meter. So this complicated looking system, we have made it like this. Okay, so we can do this for the analysis purpose. We can just remove these loadings. Okay, and we can apply this we could not do if there would have been a support here. Okay, there would have been a support at P, then we cannot do this. Okay, whenever there's a this end is free, then we can do this. Okay, we were doing it in case of beams as well. Okay, now the system is simplified and we can write it as R. Yeah, yes, is in anti-clockwise direction. Yeah, no, anti-clockwise is negative and clockwise is positive. Yeah. So it is, I have made this in anti-clockwise direction, right? Because 2000 was rotating it in anti-clockwise direction and the magnitude was 2000 into 2, that is 4000. It has greater magnitude than this one. So it is overall in anti-clockwise direction and the magnitude is 700 kilonewton meters. Sorry. Okay, so this is the final moment here. So now we have simplified this question. Now it's very easy to solve. Now, what we need to find the value of the rotation at rigid joint Q. So what can we do? We can write the equation, the slope deflection equations for every span. So in total, there will be four slope deflection equation. What will they be? MRQ, MQR, MQS and MSQ, all these things. But finally what we will do, we will apply the equilibrium equation. So equilibrium equation will be the total moment at Q. Okay, so earlier the total moment at this question, the total moment at B was 0. No external load applied at B. Okay, so total moment at B we kept at 0, but here the total moment at B is minus 700 kilonewton meter. Okay, so we can write as, for if you want to apply the use the equilibrium equation at joint Q, we can write as MQR plus M, sorry, yeah, MQS equal to minus 700 kilo, because at Q the loading is this. Okay, so we can write this equilibrium equation. I hope it is clear. So this is the equilibrium equation we can finally use. So let's solve these things. So MQR. So what will be the MQR value? MFQR. Okay, I'm writing it quickly now. MFQR plus 4EI theta Q by L plus 2EI theta R by L minus 6EI delta over L square. Let's see what are the terms we can remove. There is no external loading in the span. Okay, there is no external loading in QR, right? This 700 kilonewton meter is at the joint. Okay, it's not in the span. So this is span due to external loading in span. So MFQR is 0. Okay, now theta Q will be there. There will be some rotation at Q, but theta R will be 0. Why theta R will be 0? Because it's a fixed support. So theta R we can remove. Okay, another thing is there any settlement or something? No, there is no settlement. So this term will also be 0. Okay, so MQR we have found out as MQR will be simply 4EI theta Q over L. Very simple. Now we can find MQS. MQS is again same equation, MFQS plus 4EI theta Q by L plus 2EI theta S by L minus 6EI delta over L square. Right? Just quickly remove every extra term. Is there any external loading in span QS? No, right? So we can remove this term. Theta Q will be there. Yes, theta Q will be there. Theta S? No, because its S is also a fixed support. So theta S will be 0. Is there any settlement or sinking or anything like that? No. So this term will also be 0. Okay, so MQS we can simply write it as 4EI theta Q over L. Now we can use this equation. MQR plus MQS is equal to 700. We can keep this a minus term or we cannot, because here we are asked to find the rotation, not the sign. Okay, so absolute value we need to write here. So just ignore the sign for now. So MQR plus MQS equal to 700. So MQR is 4EI theta Q by L. MQS is also 4EI theta Q by L. So MQR plus MQS will be 8EI theta Q by L. So 8EI theta Q by L equal to 700. Or you can write the sign also. Right? Now everything else is known, just we need to find the value of theta Q. So theta Q will be 700 into just one more thing here, the units. Okay, just make sure that whatever is the value of EI na, just keep everything like that. Here the value of E is in MPa means Newton per mm square, and I value is also in to the power 4. So just keep everything in Newton and mm. In previous question, the value of EI was given in kilonewton and meter. So I kept everything in kilonewton and meter just for so that there would be no mistake. But here everything is given in Newton and mm. So just keep everything in Newton and mm only. Okay, so EI. So what is the value of E? Sorry, 700 into L. So what is the value of L? Length here is 4 meter for both the spans, right? So the length will be 4000. So 700 kilonewton meter unit was there. So converted into Newton and mm, it will be 10 to the power 6. What is the value of L? L is 4 meter, or you can write it as 4000 mm. Then 8. Then what is the value of E? The value of E was given as 2.5 into 10 to the power 4 Newton per mm square, and the value of I is given as 8 into 10 to the power 8 mm4. So just write all these things. So E is 2.5 into 10 to the power 4, and I is given as 8 into 10 to the power 8. Okay, anything else? Yeah, 8. This 8 is also there. So this 8. Yeah. So from this we can find the value of theta Q as 0.0175 radian. Please remember that this value, whenever you solve these equations, the value of theta comes in radian. But here they are specifically asking rotation in degrees. Okay, so you might have done the right answer every step correct, but if you write 0.0175 here, it would be wrong. Okay, so just listen, read the questions very carefully. So here theta q is coming as 0.0175 radian. So we can convert it into degree. How to convert radian into degree? By multiplying by 180 divided by theta. So 180, sorry, divided by pi. Okay, so 180 divided by pi. So we get the value of theta q as 1.0027. You can also try to solve. Okay, 1.007 1.0027 degree. Okay, but they are asking the rotation value up to 1 decimal place, only 1 decimal place. So answer will be 1.0. So you have to write like 1.0 as the answer. Okay, so the questions might not be that difficult, but you have to see these small mistakes. So Okay, that this will be okay if you'll solve the you have to do a lot of mock test actually, then you'll get to know all these small things. Okay, is there any problem till now? If there is not, then I'll we'll do one practice problem in which this delta term will also comes into picture. Okay, so here, yeah, so this is a question in which there's a beam A B C. So it's a propped cantilever kind of beam with overhang. So consider the beam as shown in the figure. Assume the modulus of elasticity E as 2 into 10 to the power 5 MPa. MPa means Newton per mm square. So EI is given in Newton per mm square. So I'll keep everything in Newton and mm. Okay. And modulus of, moment of inertia is given as 5 into 10 to the power 6 mm to the power 4. Okay, the next thing is so we need to determine the moment at A and B if the support settles by 80 support B settles by 80 mm. Okay, so in the span AB there is no external loading. Okay, there's a just a load here in at point C, and they are asking that if the support settles by 80 mm, this support, if it settles downward delta by 80 mm, what would be the value of moment at A? So let's do it for A only for now. Okay, determine the moment at A. So this is the question. Okay, so here whenever this overhang kind of thing is there, na, just remove it and apply the moment here, like we did in the last problem also. Na, there was this overhang part, so we just removed this part, and instead of this part we have applied this moment. Okay, so you should do that. Okay, it will simplify your problem instead of considering this BC span also. If this part is like a overhang, just remove this loading and apply a moment here. I'll tell you how. Okay, so our beam was like this. So it's A, it's B, and it's C. At C and there is a load 8 kilonewton. The distance between BC is 3 meter, and this distance was given as 4 meter. So this was the case. Just instead of this loading, apply the moment here. So what we can do, let's make an equivalent system here. So we can remove this part, BC part, and instead of this we can write it as, we can shift this load as here 8 kilonewton, and what we can do, we can apply a moment also. The moment will be 8 multiplied by 3. Moment is force into distance, so it will be, moment will be 24 kilonewton meter. So this is the equivalent system. Yes, Harini. Why we shifted, or we shifted this because because BC is an overhang kind of part. Okay, so if you can also do it, how you can do it, you can consider this as a span, and you can do it like MBA and MBC. You can consider this like that also, but it will be a little lengthy. So you can just make this an equivalent system. So I've told in the previous classes also that whenever there's a system like this, you can make it an equivalent system like this, and this will simplify your problem. In the real structure you are not doing this. Just for the analysis purpose you can do this. If you want to find the moment at A, you can make this system as an equivalent this system. So whenever we shift the loading, so here we what we did, we shifted the load from C part to D part. Okay, sorry, C part to B part. So whenever we shift a load, we apply a moment also. I've told it in the pre-stress wala class also, right? So you are asking why we did that, or is this something wrong with this? Like in this question also we did the same thing, right? 700 kilonewton meter also. One thing is that this 8 kilonewton load, if this is bothering you, this doesn't matter here. Why? Because this 8 kilonewton load is directly at the support. Okay, so this support will take up this load. Even if you do not make it, it will not make any difference. You can remove this also. So if this is fine for you, you can do that also. Just don't consider this 8 kilonewton load, because anyhow it is going, it is at the support B, and support B will entirely take that 8 kilonewton load. There will be no effect on the span AB. So if you are confused with that 8 kilonewton load, just don't make it. Okay. So you can make it like this also. I've just or you can say that you have just you have drawn the free body diagram. If you are not satisfied with this, what you can do is you can say that you have made a free body diagram. So how to make this free body diagram? For this and this is span AB, and this is span BC. Okay, we can make this free body diagram like this, right? Okay, so for span BC, here is a 8 kilonewton load, right? If I'm making the free body diagram for span BC only. So this was 8 kilonewton applied load. So now this there will be upward 8 kilonewton at B. Okay, and there will be also a moment here, and it will be like 8 threes are 24. And then we can shift this load here as 24. So from the free body diagram also, the moment at B is coming out as 24 kilonewton meters. Either you can directly make it or you can draw the free body diagram. Anyhow, you'll get the moment at B as 24 kilonewton meter. Any problem? Any issues with the free body diagram? Okay, so if you do not want to make the free body diagram, you can just, whenever there is an overhang part, just remove that part, just ignore that part, and instead of that, whatever the moment is coming, just make that. So here it is 8 kilonewton point load at 3 meter distance, so moment will be 8 into 3, simply 24. Just don't think and make it as 24 here. Is it clear? Now this is the final thing which we need to solve. So here, yeah, so here what is the equilibrium equation we can use? The equilibrium equation is MBA is 24, right? MBA, you other if this 24 kilonewton would not have been here, so MBA is 0 because it's a hinge. But here the external load 24 kilonewton is there, so it is MBA equal to 24. This is the only possible equilibrium equation here. Okay, right? So this is MBA equal to 24 kilonewton meter. Is there any confusion in this part? MBA is 24 because MBA is hinge. There is no other, there is no moment here, but we have applied this 24 kilonewton moment externally. So it's MBA equal to 24 kilonewton. Now, yeah, so MBA is coming out like this. Now we can simply use the slope deflection equations. So slope deflection equation MBA is MFBA plus 4EI theta B over L plus 2EI theta A over L minus 6EI delta over L square. This is the slope deflection equation MBA. For MBA, here is there any MFBA? Is there any external loading in the span AB? No, there is no external loading in the span. This 24 kilonewton is not on the span, it is at the joint. Okay, in the span AB, is there any external loading? No, so this term is 0. Is the theta B will be there? Yes, theta B will be there because B is a hinge support, so there will be rotation here. Theta A will be there or not? No, because A is a fixed support, so there will be no theta A, so theta A will be 0. Is there any settlement of support term given? Yes, it is given that the support B settles by 80 mm. So earlier we were always doing 6EI delta by L square as 0, but here it would not be 0. What is the sign convention for this delta term? Whenever the right hand support settles downward, the delta value will be positive. That was the sign convention which we discussed. Whenever the right hand support, so A is on the left side, B is on the right side. Whenever the right hand support settles downward, so delta will be positive. So that is the sign convention. So we can write as MBA as 4EI theta b over L minus 6 EI. What is the value of delta here? 80 mm by L square. So this is the thing. So MBA, what is the value of MBA? MBA is 24 kilonewton meter. But we are doing everything in Newton and mm. So we can write it as 24 kilonewton meter as 24 into 10 to the power 6 Newton mm. What is the value of, let's write it as this only, 4 EI theta B over L for now, and 6 EI delta or 80 by L square. So only unknown thing here is theta B. Other than theta B, everything is known. So we can find the value of theta B from here. So can you solve it, the value of theta B for me? So I'll write it as 4 EI theta B over L is equal to 24 into 10 to the power 6 plus 6 EI into 80 divided by L square. Just do it. Just I need to check whether you are solving it at keeping every units same or not. Everything else is given to you. Just need to find the value of theta B here. So what is the value of theta B you are getting? Just try it yourself. One more thing you can do here, if you want to be a little, you want to save a little time, is that either you can, what you can do, either you can find the value of theta b from here, and finally what they are asking the value of MAB, right? So they are asking the value of MAB. So either you can find the value of theta b from here and put it on the in the equation, MAB equal to MFAB plus 4 EI theta A over L plus 2 EI theta B over L minus 6 EI delta over L square. Here this term is 0. Theta A wala term is also 0 because it's a fixed support. So either what you can do, you can solve this equation and find the value of theta B, and finally you can put the value of theta B in here and get the value of MAB. Because finally they are not asking the value of theta B, they are asking the value of MAB. Okay, another thing you can do is just find the value of 2 EI theta B by L. From this equation, just find the value of 2 EI theta B by L and put it here. How? I'll tell you. Okay, it's very simple. Yeah. So here, instead of finding out the value of theta B, just find out the value of 2 EI theta B, because here in this MAB equation, we need this value, right? So 2 EI theta B of by L would be equal to, I'm just dividing the whole equation by 2. Okay, because here, yeah, 2 EI theta B by L will be 12 into 10 to the power 6 plus 3 EI by L square into 80. Okay, now I know the value of 2 EI theta B by L. I can simply put the value here and I can find the value of MAB. If you'll first find the value of theta B and then put it here, it will be very lengthy for you. If you want to save some time, then you can do that. If they would have asked the value of both theta B and MAB, then you have to solve it completely. Is there any confusion in this thing? Just to save some time, you can do this. Okay, so if you solve all this equation, if you will put the value of 2 EI theta B by L in this equation here, then finally you'll get the value of MAB as minus 3 kilonewton meter. So it will save a considerable amount of time for you. Okay, so answer is minus 3 kilonewton meter. You can try solving it yourself if you are getting the same or not. Okay. So in this question, so four options were given to us. So minus 3 kilonewton meter means anti-clockwise. So this will be the answer. C option. 3 kilonewton meter in anti-clockwise direction. Okay, so these slope deflection method questions are very easy. Okay, just you need to keep in mind this equilibrium equation due to different loadings, and you should remember some fixed end moments, no problem, and the unit thing. Finally, unit thing is very important. You need to keep in mind the units which you are using. Just be consistent with the units. Other than that, the problems are very easy. I tried to find all the problems related to slope deflection equation in gate, but I could find only 2 3 problems using this method. Okay, so just if you could get some other problems, just practice them, or practice as, using the mock test and all. Okay, so is there, if there is no confusion, then I'd like to close the session for today. Okay, any problem? S- Okay. Please ask me questions. I'm here for the questions only, because these type of problem and solution you can see in the YouTube also, because YouTube, many coaching institutes are providing solution and everything. But the main purpose of these classes are, if you are having any doubts, however small it can be, okay, anything you can ask me. Okay. Okay, then. Thank you so much. If any doubts, you can ask me in the next session also. Okay. And if you want to study a particular topic, you can tell me. Then I may incorporate that in the coming sessions also. Okay. Okay, then all the best. Thank you for listening. Okay, then bye.